Okay, welcome back, Science 10s. Mr. Thompson here. We're on section 2.4 of Unit B. This is the second part of the lesson on 2.4. Number 4 here. A baseball has a mass of 145 grams and is thrown up into the air at an initial velocity of 16 meters per second. What is the initial kinetic energy of the baseball? Our formula for kinetic energy. And we'll sub in what we have here. Now 145 grams, 0.145 kilograms. And then we have 16 squared. 18.56. And so it's roughly about 19 joules. When the baseball gets to its maximum height, what is the potential energy of the baseball? So assuming no friction or air resistance is a factor here, then all of that energy, the initial kinetic energy, becomes potential energy. And so the potential energy is calculated by knowing that it's the same as the kinetic energy. And so it's going to be this 18.56 or 19 joules. And that's at the max height. Part C, what maximum height does the baseball reach? Here's my formula for potential energy, and we just need to solve it for the height. Again, we're going to divide both sides by mg. So we're going to solve for the variable rather than putting in my numbers. You can feel free to put in your numbers if that makes you more comfortable. I have EP over mg. So I have 18.56. Notice I'm using the unrounded number divided by the mass and g. Put that in brackets. Make sure you do that on your calculation so that you don't get a calculation error. I get a height of 13 meters. Question number 5. The car has a mass of 1,200 kilograms and is traveling at 120 kilometers per hour, which is 33.33 meters per second. The driver sees a moose crossing the road and steps on the brakes. The car comes to a complete stop in 60 meters. What is the maximum kinetic energy of the car? Remember, always write down your formula. And now the substitution here. I have to use the speed in meters per second, not kilometers per hour. Okay, we get a fairly large value there. So I'm going to write it down. And then I'll put it into scientific notation. Notice I want to have, since I used 1,200 kilograms and 120 kilometers per hour, I'm going to keep this as my 3 significant digits, and this one has 4. So I would write this as 6.67 times 10 to the 1, 2, 3, 4, 5. And of course in joules. In B, how much work must be done to stop the car? Well, work is defined as a change in energy. What kind of energy are we talking about here? Well, the work is done to change the kinetic energy of that moving car. And so really, we know that the work done here is going to be the same as the change in kinetic energy. It's starting out with this value, and it's going all the way down to 0. And so the work done would be the same as answer A, 6.67 times 10 to the 5 joules. In part C, how much force was used to come to a complete stop? Well, work is defined as the force times the distance. We know the distance is 60 meters, and so that's where this is going to come in. Now I can go ahead and calculate the force. Again, I'm going to solve for the force by dividing both sides by d. Now I'll put in my numbers. I'm going to use my unrounded number and my d value of 60 meters. One 108.889. And so I'm going to round this to 2 significant digits because of the 60. So it would be 1.1 times 10 to the 4. Now, force is not in joules, it's in newtons. Okay? All right, one more question to go. Let's look at conservation of energy in a pendulum. As a pendulum bob swings back and forth, the energy changes from potential energy to kinetic energy and back to potential energy. At any time, the total energy, mechanical energy, in the system is constant. So notice the diagram here. It shows that the kinetic energy is at a max, okay, at the bottom here, and potential energy is equal to 0. As it starts to swing up, it has both potential energy and kinetic energy, kind of in the middle. When it gets to its max height, it slows to a stop before reversing its motion, and therefore its kinetic energy is 0 at that point when it stops. Its potential energy is at a maximum. Okay? Notice the idea, the formulas are very much the same, and the example number 1. A heavy pendulum is raised to a height of 16 centimeters. At the lowest point, what is its maximum velocity? So we know that the total potential energy at a max height is equal to the kinetic energy at the bottom. Okay? So I can go ahead and put in my equation as mgh and 1/2 mv squared. Now I want to solve this for the maximum velocity, so that'll be v. So I'm going to first of all cancel off mass since it's common to both sides. I can divide out the mass. The mass is non-zero, so that's okay. Otherwise, there wouldn't be a pendulum bob. And we multiply by 2 straight across, and then we're going to undo the square by square rooting. And so my equation looks like this. V is 2gh. V squared is 2gh, so V is square root 2gh. So I have the square root of 2 times 9.81 times, now 16 centimeters needs to be converted to meters, so 0.16. All of that underneath the square root. So I'll calculate this, and then I'll take the square root. I get 1.77, and so I want to round this now to 2 significant digits from the 16 centimeters. And so I would say it is 1.8 meters per second. All right, thank you for joining me.